All right, so today we're going to continue looking at identities. Okay, we've already looked at some of the basic identities, like the reciprocal. You flip sine, you get cosecant. You flip cosine, you get secant. We looked at sine squared plus cosine squared equals 1. Okay, those were your Pythagorean identities. And today we're going to look at a few different types. We're going to look at what's called the sum and difference, the double, and the half angle formulas. Okay, so a lot of formulas, but none that you have to memorize. You can make a reference sheet with everything we're going to do. So the first one deals with this kind of situation. If you have the sign of a sum, the question is, can you split it like that? And the answer is no. That you can't really use the distributive property with the word sign. It just doesn't work. Right, so what we're going to do first thing is we're going to come up with a formula. I think I'm going to start with cosine. But we'll come up with one where we have a cosine with a sum. Then we'll do cosine with a difference. Then we'll do sine with a sum and sine with a difference. Okay, the first formula I'm going to give you, it's rather difficult to prove. So I'll just give you the first one. And then the other formulas, at least two of them, we're going to prove using this one. Okay, but the proof of this, it's in your book on page 409. It'd probably take about 15 minutes to do the proof. So here's the formula for the cosine of a difference. Okay, it's cosine plus sine. Cosine of the first, cosine of the second angle, plus sine of the first, sine of the second. And all the formulas look very similar to this. Sometimes you change the plus to a minus. Sometimes things switch places. That's why it can get a little tricky to keep track of. All right, so where we can use that formula, at least numerically, is to figure out something like this. Okay, I want to find the exact value of cosine 15. Okay, and the way we're going to do it is we're going to rewrite 15. We're going to write it as a difference. Okay, but we have to pick numbers that we know how to work with. Okay, the numbers that we know how to work with, anything that's a multiple of 30, and anything that's a multiple of 45. All right, so anybody think of a way you can write 15 with subtraction using numbers that are multiples of 30 and 45? Don't think too hard about the multiples. This one's pretty straightforward.
45
Yeah. You can write 15 as 45 minus 30. And the reason we pick 45s and 30s is because those angles we've worked with before. Okay, special right triangles. So now I'm just going to expand it out, filling in 45 and 30 for my arguments. Okay, so I have cosine of the first, cosine of the second. It's going to be a plus. With cosine, it's always the opposite of the sign you had inside. If it's negative, you use a positive. And then sine of each. Sine 45, sine 30. All right, so now we need to know all of these answers exact. Okay, so either we have to memorize them, or we can type this in, get the decimal, and then we have to recognize it. 0.707. Does anybody remember what that is as a fraction? Has a square root in it. What square roots come up when you draw the 45, 45, 90 right triangle?
Square root of 2.
Square root of 2 comes out. Anybody remember how you get this from the square root of 2? Square root of 2 is about 1.4.
Square root of 2 over 2?
Yeah, this is the square root of 2 over 2. It'd be really time consuming if we had to draw the unit circle and derive this. So we just have to know it. Okay, so 0.707, that's your square root 2 over 2. About 0.866. This comes from the 30, 60, 90 triangle. What square root comes up in the 30, 60, 90?
Square root of 3.
Square root of 3. Yes, that's the square root of 3 over 2. Square root of 3 over 3 is another number that comes up, but that's usually with tangents. Okay, so these are the numbers you'll see a lot. Plus, okay, sine 45 is also root 2 over 2. Okay, and the sine of 30, that actually comes out to a nice answer. Anybody remember the sine of 30? Not 1. 0.5. That's a half. Okay. Okay, now we just multiply this out. So we're going to have a denominator of 4. That's common in both fractions. What's the square root of 2 times the square root of 3?
Square root of 6.
Yep, square root of 6. And there's your answer. Okay, so on your calculator, if you type in cosine 15, or if you type in what we have here, it's going to come out exactly the same. That's the exact answer, cosine 15.
We can find it differently if we just put cosine of 15 and calculate.
Because it's going to give you a decimal. If you type cosine 15 on one of these calculators, it's not going to give you that. Okay, and on the test, I will ask you for the exact answer, and you have to show me, how you split it up to get that. Okay. So any questions on that one? Okay, so that's cosine of a difference, and you could use that formula for any angle that you want to find the cosine of that you don't know, but you can somehow write that angle as a difference of two other angles. You just have to use multiples of 40 and 35. Okay, don't use something like 17 minus 2. Even though 17 minus 2 is 15, we don't know how to work with 17-degree angles or 2-degree angles. So you've got to use those kinds of angles.
Well, if it was like sine of 15.
We'll get to a sine sum in a second. Well, a few minutes. All right, I want to prove that the cosine of pi over 2 minus theta is the same as theta. In other words, what this is basically saying is cosine and sine are phase shifts of each other. Okay? And if you remember the graphs, they both are waves. Cosine just starts at the top, and then sine starts there. Okay? So they are the same graph. It's just been shifted a little bit. Right. How could I use that formula that we had before to prove cosine of pi over 2 minus theta equals sine theta? What could I do? That's Corey. Any thoughts? Think about what trig function do we have on the left? Cosine. And what about in the argument? What operation are we doing? Subtraction. That's cosine of a difference. Yeah, we do what we just did, except that instead of having numbers for each angle, well, one of them is a number, the other one's not. Okay, so somebody remind me, how does the cosine formula start out when we split it? Shannon?
Cosine of 2 plus cosine of 3.
Yep, cosine first, cosine second. Cosine first, cosine of the second. Is it a plus or a minus?
Plus.
Yep, it's a plus, and then it's sine. Sine of the first, sine of the second. Okay, now you can use these graphs to help you. Okay. When we're at pi over 2, what's the cosine of pi over 2? 0. Okay, that's the cosine of 9. That becomes 0. And what's 0 times cosine?
0.
So this whole part just canceled out. Let's look at sine of pi over 2. All right, so, oops, do sine. when we're at pi over 2 for the graph of sine, what value do we get for y there? 1. So all we're really left with is 1 times sine, which is what? Sine. Okay. So we just proved cosine pi over 2 minus theta is the same as sine.
Wait, why did you cross out the cosine?
Why did we cross out the cosine?
The second one.
The second one? Because we had, this was 0.
Oh, okay.
And 0 times anything, it doesn't matter. This whole thing just becomes 0 plus 1 times sine. All right, we could also look at this one. It's pretty much the same idea, except now try it with pi, and somehow everything's going to cancel out, and you're going to be left with negative cosine. So we have cosine, cosine, sine, sine. Okay, Tom, what would I fill in for my first argument? Pi. Second argument? Theta. Now do the same thing again. Pi, theta. Okay, now think about the graph of cosine when we hit pi. Where are we at on graph of cosine when we hit pi? We're at -1. You could type it in if you're not sure. Now think about the graph of sine. When we're at pi, what's the value of sine there? 0. And what's 0 times sine? So this whole second part cancels out, and all you're left with is negative cosine. So we just proved that cosine pi minus theta is the same as negative cosine. Questions on that one? All right, now we're going to look at where the cosine sum formula comes from. Okay, but there's two things we need to know to do that. Okay, these two things. It turns out, if you want to take the cosine of a negative angle, you can get rid of that negative, and it doesn't make any difference in your answer. Take the cosine of -30, take the cosine of +30, the answers come out the same. So with cosine, if you have a negative in your argument, you can actually just get rid of it. It doesn't matter. With sine, you can't get rid of it, but you can move it to the front. Okay? So for example, if I did sine of 30, sine -30, they're not going to come out the same. But what I can do is just put a negative in front of my answer. Okay? Any question on those two formulas? So with cosine, you just get rid of the negative. With sine, you can move it to the front. All right. Keep those in mind as we go through this. Okay, we're about to come up with the formula for cosine of a sum. What's the only formula that I know right now? Cosine of difference. So somehow I have to use that. Anybody think how we can write alpha plus beta as a difference? Just a little trick with signs. But it's kind of confusing when I say signs. Just a little trick with SIGNs. Yeah, I'll spell it out when it's confusing. All right, alpha minus what?
Not like the alpha plus beta, and then you minus 1. I have no idea.
Any other thoughts? Just like if I said write 2 plus 3 is subtraction.
2 minus 2? Or 3 minus 2?
You're going to get the same answer, though. How could you write 2 plus 3 with subtraction?
6 minus 2?
You got to use the same numbers.
And get the same number?
Well,
3.
or they're opposites.
3 minus negative 2 would equal 6, right?
I would do it that way.
Equals 5.
2 minus negative 3.
I'm stupid.
Okay.
Yeah.
So how could we write?
Alpha minus negative beta.
Yeah. Now we just wrote a sum as a difference. Now we can use our formula for the difference. There's my first angle. There's my second angle. Okay. So now we'll go through it, see what happens. Okay, we've got cosine of the first, cosine of the second. Plus, DJ, can you fill in the rest for me?
Yeah, be sine alpha times sine beta.
Sine,
With the B, the other one. Oh, opposite. Oh, no, sorry, it'll be. Negative sine of the B, or whatever, the beta.
not negative sine. Where's that negative go for now?
Just
No, not in front of sine. Just like it did with cosine.
It's just negative beta.
It's just negative beta. Okay?
That's the negative sine.
Right, this negative, we're going to do something with it in a second. Okay, but for now, it's just cosine of the first, cosine of the second, sine of the first, sine of the second. Just remember that that minus sign is part of it. Okay? It's whatever it is before the minus sign and whatever's after the minus sign. That's what you plug in. All right, what happens in this first part? Anything there that I can simplify?
You can just get rid of the negative, right?
I can get rid of the negative on that beta. Yep. So cosine alpha, cosine beta.
Wait, how do you get rid of the negative?
That's a rule.
Cosine of negative x equals cosine of
I
x.
think we looked at that.
Oh, okay.
Might have been a few chapters ago. And what about the negative on the sign?
You put it before the sign.
Yeah, we can put it in front. We can't get rid of it, but we can put it before the sign, or we can just put it before the entire thing. So what we end up getting is minus sine alpha, sine beta. Okay, there is your cosine sum formula. So it's cosine cosine minus sine sine. Okay, we're not going to have to go through that derivation again now. We're just going to use it to figure something out. Okay, what angle do you think I could figure out now? Think of how we did 15 before. What do you think an angle that this formula would allow me to do would be?
Oh.
I'm thinking of a number. Thinking of a number you can get with angles that are multiples of 30 and 45. 75. Yep. That's the one we're going to do. Okay, you can't really get, well, you might be able to think of a way to write 75 as a difference. If you could think of two angles that are multiples of 45 and 30. Subtract one from the other. Yeah, actually, I think you could write it as a difference if you did 135 minus, no, that wouldn't work. That'd be 105 minus 60 work? Yeah. So you could do it as a cosine difference if you use these two numbers, or you can do it as a cosine sum if you use what two numbers?
30 and 45.
45 and 30.
I mean 30, not 40.
Okay, so you could do it either way, but let's practice it as a sum. Okay, so Olivia, what's going to be my argument the cosines, the first two?
Cosine 45 and cosine.
Yep. Is it a plus or a minus when we're doing a sum? Yep, when we split it up, it's a minus. Just got to remember that. And now copy down what you did for the first part. Just change signs, cosines to sines. Okay, hopefully remembering what we did earlier. What's cosine 45?
Two.
2.
Square root of 2.
Cosine of 30?
Square root of 2.
3 over 2. Sine of 45? And the sine of 30? 1/2. So you get a very similar answer to what we did before. Except now that became a minus.
Hey, why is it gonna fall on the law?
2 times 2 gives me a 4.
Got it.
Yep. So we had a 4 on the denominator on the left, 4 on the right. So just common denominator. Okay. Any questions on that one? Okay, everyone's all right with that? So one nice thing about this is you can type this in. Type in cosine 75, make sure they match. You can always double check your answer. Okay, now we're going to figure out the sine sum formula. Okay, we proved this back in example, I think it was 2a. Cosine of pi over 2 minus theta equals sine theta. Okay, we're going to use that fact that we proved in this problem. So that fact said that if you want, you can rewrite sine of an angle as cosine of pi over 2 minus that angle. What's the angle that I'm going to be working with in this problem? The entire thing. Alpha plus beta. All right? So this is my theta, this whole thing. So I can rewrite that as cosine pi over 2 minus my angle, which in this case is alpha plus beta. Now, if we wanted, we could do this every time. Every time that we have a sine of a sum, we could rewrite it this way and just use the cosine difference formula. But it's going to be a lot faster if we do it generically one time and actually just get a formula for the sine of a sum. Then we don't have to think about trying to do it this way every time. Okay. What do I have to do with that minus sign? I got to distribute it. And I'm going to write it as cosine pi over 2 minus alpha minus beta. Okay, so I'd have a minus alpha and a minus beta, and I grouped these two together. Okay, and you'll see why. So now we have cosine of a difference. Okay, so let's write that out and see what happens. So we have cosine, cosine, plus sine, sine. Okay, Heaven, what's my first argument? Yep. Oh, pi over 2. What's that minus? And help her out. Yeah, it looks like the fish. Alpha. Thank you. Pi over 2 minus alpha. Pi over 2 minus alpha. Okay, and my second argument? What is it? Yeah, just what comes after the minus sign. Beta. Okay, look at this part. cosine of pi over 2 minus alpha. How can we write that more simply? We proved this is equal to something earlier. It's sine, right? The cosine of pi over 2 minus something is the same as the sine of that something. Okay? So just write sine alpha, cosine beta. Now, this one we didn't actually prove, but what do you think the sine of pi over 2 minus alpha is the same as? It's kind of the same reasoning as this one. Cosine alpha. Yep. The sine of 90 minus something, if you did it in degrees, is just the same as the cosine. And sine we can't really do anything with. Okay, so here is your sine of a sum. Okay, that's the sine sum formula with its derivation.
Why do you take the negative into account?
The only time you use the negative is if you have two of them like that. Okay? So when we had, was it this one? Yeah. It's whatever comes after the minus sign. So if there's a negative after the minus sign, then you use it. Otherwise, if there's no negative, we just use whatever's after it without the negative. Okay. Any other questions on that? Yeah.
So how do you go from having cosine pi over 2 minus alpha plus beta and having
This comes from right there.
no in between those?
In between these two?
Like, because you had cosine or pi over 2 minus alpha plus beta, then you change it to pi over 2.
Oh, from this step to this step?
The top one, go up.
From this one to this one?
Yes.
I just distributed the negative. That's all. Pi over 2 minus alpha minus beta. Minus alpha minus beta. That was it. Okay, good question though. Any other questions on this? So that's your sine sum formula. Any guess what the sine difference formula is going to be? It's just going to be the same thing with a minus. So it's always sine of the first, cosine of the second. Cosine of the first, sine of the second. With the sine difference, you use a difference. With the sine sum, you use a sum. Okay, so now you have all four. Okay, and what we could do with this one, now you could find, somebody asked me about sine of 15 or sine 75, something like that. You could use these formulas to do exactly the same thing we did with cosine. Okay, and we're not going to go through the proof of the sine difference formula. Okay, any question on the sine difference formula? Okay, what if I asked you to find sine 105? How would you do that? And there might be more than one way. Yep.
75 and 30.
75 and 30. Okay, now you could, as long as you knew the answer for 75, because 75 is not a multiple of 30 or 45. But if you did that in a previous problem and you already had it, you could use it here. Okay, if you didn't have it, then we would want to try to do it a different way. And it's still going to be something ending in a 5 here. But make the second one a little bigger, make that one a little smaller, and we could have it. Matthias?
Can't you do 135 minus 30?
Yeah, that's what I was
Okay, so if you're thinking the root of a difference, That's a multiple of 45. That's a multiple of 30. Perfect. How about if you were thinking a sum? Yep. Yeah, go ahead, Olivia. You could do 45 plus 60. Both problems would give you the same result. Okay? Any questions on how you do sine a 105? Either way. Okay, what I do is, if I don't remember 135, I could type it in. Okay, that's going to be a root 2 over 2. Okay, the other number that's going to come up is cosine 135. That's a negative root 2 over 2. So you see the same numbers, root 2 over 2, root 3 over 2. It's just now, because you have bigger numbers, you might get into negatives. Okay. All right, these aren't used as much. And there's actually a way we could avoid using tangent. Does anybody remember how you can write tangent with sine and cosine? Right. So technically, if I asked you for, let's say, tangent of 15, this would be longer, but you could do sine of 15 and then divide by cosine 15. That would work. But then you'd have to use one formula for sine and one for cosine. Okay, let's try tangent of 15, but I'm not gonna do it with sines and cosines. I'll actually use one of these formulas. Okay, how could we write 15? You can do it as a sum or a difference.
45 minus 30.
Yep, I do it as 45 minus 30. So we're using the tangent of a sum. So tangent of the first plus tangent of the second. Over 1 minus tangent of the first times tangent of the second. Okay, tangent of 45. Anyone remember what that one is? It's the angle, think about, it's in an isosceles triangle, and you're dividing the opposite and the adjacent sides in an isosceles triangle. So if those two sides are the same and you're dividing them, what would you get? 1. Okay. Again, you don't want to get too bogged down in trying to remember what these are. Some of them you really should memorize or be able to recognize the decimal really fast. What's 0.577? Square root of, you're in the 30, 60, 90 triangle, so what square root comes up? And no, that one's always 3. Okay, square root 3 over 3 comes up a lot. Okay, what's tangent of 45? 1. What's the tangent of 30? Okay, what I would do on the top and the bottom here is triple everything. That's at least going to get rid of my denominators. What would that leave me with in the top?
3 plus
And the bottom?
3 minus the square.
Yeah, there's a little more we could do with that. If you multiplied, maybe I should show you just for arithmetic purpose. If you multiply top and bottom by the conjugate, it would clean up a little nicer. The conjugate is you just take what's in the bottom and change the sign. 3 plus root 3. Okay, does everyone remember multiplying conjugates, foiling it?
No.
No? All right, we'll go through it really quick. In the bottom, what's 3 times 3? 9. 3 plus root 3, 3 minus root 3? 0. Negative times a positive is a negative. What's the square root of 3 times the square root of 3? 3. Okay, so the bottom actually comes out pretty nice if you multiply by the conjugate. The top, you're going to get 9. 3 root 3 plus 3 root 3. How many of those? 3 root 3 plus 3 root 3. Graham just said it.
Said 96. It's one of those two.
6 root 3, right?
Okay.
3 root 3 plus another 3 root 3. That's a 6 root 3. And then root 3 times root 3. 3. So it actually cleans up pretty nice, and we only end up with one root. We could write it as 12 plus 6 root 3 over 6. And now you could divide each one by 6.
You get 2.
So if you clean it up and multiply top and bottom by the conjugate, it comes out pretty nice. 2 plus the square root of 3.
Will you accept the top one?
This one?
Yeah.
It depends. If they say to not leave square roots in the bottom, that's how you have to fix it. Yeah.
I thought you can separate addition and fraction like that.
You couldn't do what?
Like you just divide everything by 6.
Yeah.
I thought you can separate the addition and top.
As long as there's a 6 here, here, and there. You can do it in all those spots. If that 6 wasn't next to the root, I couldn't do it. You can't touch any numbers that are under the root, but the ones outside are okay to simplify. Yep. All right, so this is really just playing around with arithmetic. If you got this far, that's okay. Any questions on getting at least this far? What's that?
You put the formulas back up.
The formula? Yeah. Okay, if you really don't like the tangent one, I suppose you could do the sine of 15, do the cosine of 15. I don't know if that's any shorter than this. Probably not. All right, so there's your sum and difference identities. Okay, the next group of identities we're going to look at are what are called the double angle identities. Okay? You've got an angle and it's been doubled. And a lot of times what we want to do is get rid of this 2. Well, it'd be nice if we could just take the 2 and just stick it in front, but we can't. Okay? Even geometrically, this doesn't make sense. This is a period change, what's on the left. That's going to compress the graph horizontally. What does putting a 2 in front do? Stretch it vertically. So even just from a transformation standpoint, these aren't the same thing at all. Okay? So we're going to prove that this is what sine 2 theta equals. 2 sine cosine. So if you want to get rid of the number in front of the theta, you can do it. But usually it looks messy. Okay? It starts to get a little messy. And the hardest problem we're going to do today is going to be one that involves a double angle. Okay, I'll let you know when we get to it. All right. So in order to prove this, I need to rewrite 2 theta as something simpler. Anybody think, how could you get 2 theta? Like what calculation would you have to do, and that would be the final answer? Theta times theta. We're on the right track, but that'd be theta squared.
Theta plus theta.
Right. Could do it as theta plus theta. Now, this has a name. What is this on the left-hand side now? Yeah, it's the sine sum formula. Okay, we have something for the sine of a sum. What's going to be nice here is the first angle and the second angle are the same. Okay? All right, so sine of a sum. Sine of the first, cosine of the second. All right, so take sine of the first, cosine of the second, plus cosine of the first, sine of the second. Okay. Cosine of the first, sine of the second. Okay. So the first one is sine times cosine. The second one is also sine times cosine. How many sine times cosines do we have? 2. 2 sine cosines. Now the second one is in a different order, but that's the commutative property. You could switch that. Okay. That's the only double angle formula we're going to prove like that from scratch. Okay, so there's your double angle identity for sine. And for sine, that's the only way we normally write it. Cosine, we have some choices. There's actually 3 ways you can do the double angle formula for cosine. Does this look kind of like something we've seen before? It's almost, but not quite. Yeah, this does look like one of the trig identities. Anybody remember the one that it looks like? Yep, sine squared plus cosine squared equals 1. Perfect. Let's, no, equals positive 1.
No, I mean, this one.
No, you can't do anything with that. That's it. Nice try. Let's get rid of this. Okay? What I'm going to do is solve this formula for cosine squared. What would you get if you solve our trig identity for cosine squared?
Negative sine squared. 1 plus negative, or 1 minus negative sine squared. 1 minus sine squared.
Yeah. Just bring that sine squared to the other side, and it's 1 minus sine squared. Now, if you plug that in right here, that's going to give us the next version of the formula. So if you plug that in, you'd have 1 minus sine squared minus sine squared. What would that be? 1 minus sine squared minus sine squared. Yeah, 1 minus 2 sine squared. Okay. Now, if you rewrote this Pythagorean identity the third way, got sine squared by itself, it's basically the same thing, just kind of flips around and it's cosine squared. Now again, you don't have to memorize any of these identities. Okay? We're just going to use them. Okay, so there's the 3 versions for the double angle formula for cosine. And for tangent of 2 theta, there's 12 versions. No, I'm kidding, there's only 1. That's it. You don't have to worry about that. Okay, that's your only double angle formula for tangent. I can't think of any problems where we're really going to be using this one. In the next example, the next 2, I will use the sine and the cosine one. Okay, also at this point, we're not deriving any of these. We're not deriving these. Okay, for today, I'm going to give you, I still have a few more formulas, but we're done deriving because they just start to get really complicated. Okay, so any questions on the double angle identities? Okay, they take an argument that has a 2 in it, and they get rid of the 2. It's not always pretty, but they get rid of the 2 for you. Okay, and now you just have thetas. All right, so we're going to kind of warm up using double angle formulas, we're going to start with this one. And then we'll get into one that's, it's pretty lengthy. Okay, it'll probably be, it'll definitely be the hardest problem we do all week. Okay, I'm just letting you know. All right, let's start with this one. They want us to write this expression with just x's for the arguments. Okay. Does this first term already fit what they're looking for? writing things with just sines x's and cosine of x's? Yes, it's just a cosine x. Double, but that's fine. The key is they don't want any numbers in the argument. The first term is fine. Okay. The second term is not. Anybody tell me how I can rewrite sine 2x so that 2 is no longer in the argument? Brad?
Sine x plus or
No, sine x plus sine x would be 2 sine x. Remember, we talked about that. That doesn't work. That is not the same as that. Yep. What's our formula for sine 2x? It's the one we proved. Shelby?
No, I don't got it.
No?
Two sine,
2 sine cosine. Okay, sine 2x. Right there. 2 sine cosine. So we just substituted this in for that. Any question on that step? Okay, and now what do these both have in common we could factor out? 2. Yep, even more. Cosine x. Okay, if I factor out a 2 cosine x from the first term, what does that leave me with? 1. And what if you factor it out from the second term? Sine x. And that's it. Technically, we had answered what they wanted us to do at this step. But if you can simplify it or factor it, that's usually a good thing to do. Okay, this is probably about the difficulty of one you'd see in the homework and on the test. About that maybe you'd have a cosine 2x and a sine 2x. So it might be one step harder than this, but it will not be as hard as the next one I'm going to show you. Okay, any questions before we look at the next one? All right, so this one, anytime you have an odd number, that's a pain. Okay, if this was a 4x, I think that would actually be easier than a 3x. Potentially. Yeah. What ends up happening is we're going to have to rewrite this 3x. Okay? But let's start with the first term. That one's pretty easy. Okay, how do we rewrite sine 2x? 2 sine x cosine x. And now the problem is we don't have a triple angle formula. It exists, but I mean, there's only so many we can study. We can't study one for every single number. So somehow we have to break down 3x. Anybody think of how we can write 3x? And we're going to use one of our first formulas we learned today. Yep. Yep. 2x plus x. Okay, now I'm warning you, the algebra here, it gets pretty bad pretty quick. Okay? Okay, it's not hard, but there's a lot of stuff. Okay, this first term is just going to kind of hang out right there. Now we need to split this using our cosine sum. So that's cosine, cosine, minus sine, sine. Cosine, cosine, minus sine, sine. Okay. Any questions up to that step? Just split that second one with the cosine sum. Now there's two things here that are still not the way they want. That and that. Okay, we have 2's in both of those arguments. But at least we don't have 3's. Okay, we got it down to 2's. All right, so just copy down the first part. That's fine. Okay, cosine 2x. We have three ways we can deal with that. Okay, it turns out in this problem, that's going to be the best way to do it. The reason I'm picking that one, well, a couple reasons. One, it only has one trig function in it. If you use the top one, okay, it's got two. Okay, so try to pick something with one. And the other reason why I'm picking sine squared, well, you'll see in a second. Okay, so we're going to write cosine 2x as 1 minus 2 sine squared. 1 minus 2 sine squared x. Now we got to be very careful, because what is this still multiplied by? What was next to it up above? Cosine x. That's now distributed, okay, because you split what you had, but it was all multiplied by cosine x. That's a mistake sometimes I'll see. Okay, but it's actually good for now. Just leave it factored out. Don't distribute it. Okay. Now the second one. Okay. I'm going to write it up here. What's sine 2x? 2 sine x cosine x. So if you had 2 sine x cosine x times sine x, what would you get? Yeah, you've got 2 sine cosine sine. If you've got the sine twice, it's sine squared. I'm just doing that because it does save a little bit of writing. And I'm hoping you see something in a second. Okay, any questions on that? Now, the only thing I'm going to do in this next step is that. Okay, so what I think I'm going to do, let me just write out what that would be below it, rather than rewriting the whole thing again. Okay, and then you'll see what happens. You would get cosine x. Now watch what happens here. Minus 2 sine squared cosine. Okay. Okay, so this is gone. And now replace it with that. Okay, now I'll write everything neatly. 2 sine cosine plus cosine. And now this last part, these are like terms. Minus 2 sine squared cosine minus 2 sine squared cosine. What would that combine to? Careful, not positive 4. Negative 4. Anything else? Sine squared cosine. Okay, so really we're playing with a lot of algebra here. We're just combining like terms, we're distributing, we're just doing it with trig functions. Okay, it's all algebra. This might be something you have to go back and look at it a second time. It usually doesn't make sense the first time through. All right, now, what are we solving for? It's always good to look at. Solve for the zeros. So this is equal to 0 at every step. I'm not going to fill it in for every step. What do they all have in common?
Cosine.
Yep, they all have a cosine x. So I'm going to factor that out of everything. Cosine x. And I'm going to write it in descending order. Okay? What would you get if you factor cosine x out of the last term? Sine squared x. What would you get if you factor it out of the first term?
2 sine.
Plus 2 sine x. And what would you get if you factor it out of the middle term? 1. Okay, Okay, and the reason I wrote it in descending order is I'm hoping you see something. That's a quadratic equation. Yeah. When you have something squared, the something, and then the 1. Okay, that's a quadratic formula. All right? So we'll come back to using quadratic formula on that in a second. But if you can get this far for this problem, that's pretty amazing. Okay, that's good. All right. Now, we've factored. Okay? We're multiplying two things together, and we're getting 0. What does that mean? One or both of them are 0. So either this equals 0, or the second thing equals 0. Okay, for this one, I'm just going to think about the graph. Where's the two spots that cosine of x hits 0? Yep, and the book writes these as decimals, so just to match up with the answers that they're going to give us. Okay, there's one of them. That's pi over 2. What'd you say the other one was?
3 pi over 2.
That's 4.71. You could check it. Okay, so this part of this factor gives me 2 of the answers. Okay, the next part is the quadratic formula. Okay, does anybody recognize what's A? What's B?
2, 2.
C?
1.
1. Now, when we plug all this in and we solve, we're going to get a number just like the quadratic formula, but you're not solving for x. What are you solving for in this problem? Sine x. So when we're all done, it's going to be sine x equals, not x equals. That's important. Okay, let's just real quick go through the quadratic formula. So we get negative b plus or minus square root of b squared minus 4 a. I don't even need c because it's just times 1 all over 2a. Yep, I think I did everything out there correct, right? Yeah. Minus a minus becomes a plus. What's 4 times positive 4? 16 plus 4? That's the square root of 20, which is 2 root 5. So I added it and reduced it at the same time. That's negative 2. And if I want, I can cancel what from everywhere? A 2. So negative 1 plus or minus root 5 over negative 4. All right, so we can kind of see where two answers would come from. Negative 1 plus root 5 over negative 4, negative 1 minus root 5 over negative 4. Now, that's equal to what? X or? That's sine x. Okay. Nope, just sine x. Okay, what I'm going to do is, let's get the decimal for those. Both of them. Okay, so we've got negative 1 plus square root of 5 divided by negative 4. So I have sine of x equals negative 0.309. Okay, I'll solve that in a second. Sine of x equals, okay, do it again, negative 1 minus square root of 5 divided by negative 4. 0.809. So now, in my head, I'm starting to think of this diagram. This is where the other 4 answers come from. There's 2 quadrants where sine is equal to a negative. Here and here. And then there's 2 quadrants where sine is equal to a positive. 3 and 4. Those are all my answers. Not quadrants 3 and 4, but answer 3 and answer 4. Okay. That's where the other 4 answers are going to come from. Let's just at least go through one of them. We don't We have to go through all of them. That's actually the last problem we're going to do. So we'll do as much as we have time for. All right. How do you get rid of sign here? What do you use?
Inverse sign.
Yep. Take the inverse sign of negative 0.309. And they gave answers in radians, so we'll stick with that. Second sign. Negative. Now, they said the answers had to be between 0 and 2 pi. This isn't wrong. It's just in the wrong period. Okay, so we're still going to write it down, though. Negative 0.314. Okay, and remember, that's my reference angle. Okay, this is an angle in quadrant 4. If you drew a triangle, negative 0.314 is right there. It's just into the 4th quadrant. So I just found that answer. What other quadrant did we say sine is negative in? 3. What do you do to get an answer in quadrant 3 with my reference angle? Remember what you do in quadrant 3? If you can. In quadrant 2, it's pi minus your reference angle. How about quadrant 3? 2 pi minus, that's for the 4th quadrant. We've got that one. Pi plus. So my other answer should be, hopefully, let's just use decimals, 3.14 plus my reference angle of 0.309. Actually, what was my reference angle? 0.314, sorry. It's confusing when your inverse sine and your sine, they're almost the same number. All right, so let's see if we get some of the answers we're looking for. This 3.46, I'm thinking that's going to be this one, right? Let's check it. 3.14 plus 0.314. 3.45. Okay, so there's 3.46. Now, so we've got that one. Negative 0.314 is not listed. Okay, because they want all the answers between 0 and 2 pi. So how often does sine repeat itself? Every 2 pi. So if you add 2 pi to that, that's going to tell you when the next occurrence of it is. So let's just take 0.314 negative, add 2 pi, and that's going to tell us when it occurs in the next cycle. 5.97. There's that one. Great. So we got those two. Okay, and the last part, let's look at that one. Sine of x equals 0.809. What quadrants am I looking for here? Good. We're looking for a first and a second quadrant answer. Okay, let's just take inverse sine of 0.809 and see what we get. Inverse sine 0.809. We get 0.94. Okay. Is that in, what quadrant is that in? 1. Yep, where they're all positive. Now I'm looking for an answer in quadrant 2. Should be 2.2. How do you get an angle in quadrant 2? Pi minus what? Pi minus my reference angle, which we found was 0.94. I didn't write it down because we already had it. I wrote it earlier. Okay, let's try that. 3.14 minus 0.94, 2.2, 2.2. Okay, so again, that's a very, very hard problem. There's a lot, just from the formulas of breaking down the 2x and the 3x, never mind all the stuff from algebra 1 and 2. Quadratic formula, and then this diagram. So if that's confusing, again, don't worry too much. It's a very hard problem. But if you could at least get to this step, that would be good. Okay, being able to just use the identities to get here. If the quadratic formula confused you, that's okay. We're going to practice that more later on. Okay, so just see if you can at least do that part. Okay, just that part. All right, so any questions about what we did there? Like in terms of like what the question was asking, finding the roots. All right, so if we graphed it, how many times would it cross the x-axis? 6 times. Yeah, these should be the 6 spots. Okay, not every equation you can solve algebraically. Okay, some of them become really much harder than this, if not impossible. So we're going to stick with equations, especially on tests, that are easier than this. Okay, you would never have one this hard on a test. It's a very hard problem. Right, and the last formulas, I'm just going to give them to you. If you want to write them, it's up to you, just so you have like a complete notebook of all the basic trig identities. You got your fundamental, your sum and difference, double angle, and half angle. Okay, those are the ones that are used in trig most often. Okay, I don't think we're going to do anything with half angle in this class. But it might be nice to have them as a reference, like if you do take calculus next year, and you need these. It's a chance they could be in your calc book. If not, you could at least have a place you could find them in your pre-cal notebook. But I'd say that's the only reason I would write them down. If you're not going to need them next year, then don't worry about them. Okay, the other, I guess the only practical thing you really could do, like in this class with them, you could find the cosine of 15. Okay, remember when we did it as a difference, 45 minus 30? How could you write 15 as a fraction with a denominator of 2?
30.
Yeah. So the top, your theta, the top is 30. So if you filled 30 in for your angle here, you could actually find the cosine of 15. Okay, using this formula instead of the difference. I probably would just use the sum or difference. These are definitely not formulas that I memorize. In fact, if you ask me what one of these was, off the top of my head, I don't know. Great. So that's it for identities. Okay, there are no new identities we're going to learn in the rest of this chapter. Tomorrow, we'll practice a little bit more with algebra. Okay, but I'm going to give you guys like the last 10 minutes or so to 8 minutes. You can start the homework. Okay, and the homework is on 417. And let's see. Okay, I want you to try 1 through 5, 9 through 11, 17, 18, 29, 31 part A, 37, and 41. These are very fast. Okay, the last 5, those are the ones that might take a little longer, but nothing even close to what we did in class.